Hello, welcome to this short class. Today, we're going to study the interior of giant planets and their evolution, also how they couple with their atmosphere. And specifically, I'm going to talk about how we've been able to partially unveil Jupiter with Juno and what are the consequences for giant planets in general. And this is part of the school on planets, exoplanets, and their systems. If I get that to move on, this is the outline. So I'm going to start with the reasons why we're studying giant planets, then explain a little bit some basics about the formation of giant planets, give some details about mission Juno, how we model the interiors of giant planets in general, and then we're going to see the results we obtained on Jupiter's interior structure, Jupiter's zonal flows, its inhomogeneous deep atmosphere. That's something very important, I think. And then what are the consequences for giant planets in general, including exoplanets, and why we need a mission to Uranus or Neptune. So let's get moving. Why do we study giant planets? Well, we study giant planets firstly, I think, because we need to complete the inventory of what's in our solar system. They contain a lot of mass. Jupiter is 300 Earth masses, Saturn is 100. So all in all, giant planets possess 99.5% of all the mass in the solar system except the Sun. And their composition is very uncertain. We know that especially Jupiter and Saturn contain mostly hydrogen and helium, but they contain a lot of heavy elements, and we don't know precisely how much. Prior to Juno, we believed Jupiter could contain as little as 10 Earth masses or as much as 40 Earth masses in heavy elements. So it's a huge uncertainty for formation models and also for all the rest to understand the atmospheres, how these kind of planets evolve. Giant planets are also very numerous, we know, in the galaxy, especially if we include the ice giants, the likes of Uranus and Neptune, which may be among the most abundant planets in the galaxy. And in the sample that we can observe and that we can characterize, giant planets are dominant because those are, for the moment, the easiest targets, and this will remain so for a long time. And so it's very important to be able to understand the observations that we're getting and to learn about planet formation, about atmospheric dynamics from a very rich source of information. We have now thousands of objects and hundreds of giant planets that we can, for which we have small enough error bars that we can characterize. So on one hand, we have very detailed information that we can get in our solar system, and then we have statistics from a much larger sample in our galaxy. So it's kind of the best of both worlds, and a really timely period to be interested in those objects. So giant planets are important, of course, to complete the inventory in terms of Z elements. When you think of the Sun is about 300,000 Earth masses. It contains about 1.5% of heavy elements or metals. So that's about 5,000 Earth masses. When we look at systems information, the central object, the protostar, is already generally mostly formed. It's at least 90% of its final mass. And so we expect that there's only 10% of this initial amount that you can draw from, and so that there's about 500 Earth masses available in Z elements when you begin really forming planets. So when we look at our solar system, we know that there's about 100 Earth masses in heavy elements, and then So we're not counting hydrogen and helium. And then when we look at things that have been ejected from the work of, for example, Andre Isidoro, we can estimate that about 100 to 200 Earth masses were present initially. So led to real planet formation. So assuming that solids started from forming planetesimals no earlier than when the disk was 0.1 solar mass, it means that about 20 to 30% of solids must have formed planets. And most of these solids are either have been ejected or are within the giant planets. So we need to pay special attention to those. We can look at their atmospheres, and in our solar system, we have relatively detailed constraints, although we cannot see all the elements that we would like to see. So this table is a few years old. It has evolved slightly, but the important part here is that roughly, if you look at Jupiter's atmosphere, you have abundances of elements that are about 2 to 4 times solar. In Saturn, you're about 5 to 12 times solar. And in Uranus, Neptune, you're 20 to 90 times solar, at least for methane and carbon that we see in the form of CH4. The other elements, like water, so which is the most abundant molecule bearing oxygen, is unfortunately buried deeper, so it's very hard to constrain. But this is the global picture. So how do we explain that? We'll come back to that a little bit. There's interesting questions that you can ask and relate to the origin of our solar system, thanks to measurements done in giant planets. For example, with the Galileo probe, we measured that Jupiter's noble gases are also enriched by this factor 2 to 3 times solar. So it's not only carbon, nitrogen, sulfur that are enriched, it's also noble gases. Noble gases are very hard to trap. You must go down to very low temperatures in order to embed them into solids. And so that was a big question. And how can you deliver them? So there's several mechanisms that have been proposed. I'm not going to review that, but the one that I prefer is the one that I proposed with Ricardo Hueso. And it's simply to invoke a photoevaporation of hydrogen and helium in the proto-solar disk. So because grains these disks can be quite extended, and so you can have very cold regions. Now more observations are showing that, which are at temperatures of 20K, something like that, where you do have the temperatures to trap these noble gases, and then you can transport them to the midplane and to the inner solar system, while at the same time you're evaporating these layers, which are at high altitudes in the disk or really in the outer regions, and which are mostly free of these grains that have settled. So that's a mechanism that can enrich everything except hydrogen and helium by these factors. And so by trying to measure that in other planets, unfortunately we have this measurement only in Jupiter because these noble gases are so transparent. This would provide the means to test this particular mechanism and others like clathration in planetesimals. Then there's another example of a problem in which giant planets are important, and it involves the sun's composition. So it's been shown that the sun lacks refractory elements compared to its solar twins. So you can see in this diagram, as a function of condensation temperature, you have less refractory species then you have things like oxygen, carbon, and nitrogen that we call ices. And this may be explained, again, it's not the only explanation, but it is a possible one, by planet formation. So if you embed a lot of solids into the giant planets, and if it's mostly rocks, um, so the ice to rock ratio in giant planets is very low, of order 0.2, then this is the way we showed with Masanobu Kunitomo to explain this observation. Unfortunately, we don't know the ice to rock ratio in giant planets in our solar system or in exoplanets, but maybe we'll have the means to get that in the future. And this would be a very, very interesting measurement. Okay, so now let's look a little bit at the basics of giant planet formation. So I'm going to go very rapidly through the different steps. I believe Alessandro Morbidelli will talk about that more in this school. So basically, we have initially a circumstellar disk that forms from a collapse of a molecular cloud core. This takes only a few 100,000 years. This is very fast. Then the idea in the standard model is that we should form planetesimals of 1 to 10 kilometers rapidly so that we avoid losing them onto the central star. There's been more work on that, obviously, since then, but I'm just giving the basics. Then, from these planetesimals, you can enter into a phase that's called runaway growth, in which gravitational focusing mean that large embryos grow at the expense of small ones very rapidly, again, in a few 100,000 years. But then, rapidly, because of the interactions between the different embryos, this rapid growth phase stops, and you have a slower growth of the so-called oligarchs, so the larger bodies that excite each other dynamically. And it leads to the growth of moons and objects that can be as large as a few Earth masses at several AU in the standard picture on a million-year timescale. So this is the base for the formation of giant planets. You have these embryos that are present in a disk with gas. We know, of course, that we need to form giant planets early on when the gas is still present. So in the first few million years of the evolution of the systems. And what happens is that past a certain mass that will depend on the energetics of the system, on the amount of planetesimals that are created by the core, you will start to be in a phase in which you don't have a hydrostatic equilibrium solution between the gas outside this growing core and the disk. So this was shown by Mizuno in 1980, and this has been revised by Masahiro Ikoma here in this paper in 2000, and it shows this critical mass as a function of the rate of growth of the core in Earth masses per year. So this is 1 Earth mass per 10 to the 10 million years. So it's a very slow growth. Then you can have very low values of around 1 Earth mass, and those are different treatment of the opacities. And then for higher values, you get to critical core masses of around 10 Earth masses. So it means that as soon as your core passes this threshold, you will begin accumulating hydrogen and helium much more quickly. And then the envelope can grow onto the core, but, and this is an important point, this takes time because the envelope needs to cool before it can really contract and lead to the formation of the final giant planet. And this was actually shown in this very, very famous paper by Jean Pollack et al. In 1996, showing the different phases of the growth of the giant planets, the growth of the core here, then the phase 2, in which the envelope grows by cooling and planetesimal accretion, and then a third phase after this crossover mass, when the envelope mass becomes of the same order as the core mass, then the planet somehow must detach from the disk and really contract rapidly. So, of course, modern models of planet formation include several complications. I don't have time to enter into any details there. There's an evolving planetary disk. Planet migration is very important. There's a population of solids that includes different sources: dust, pebbles, and planetesimals. The big change in the last decade has been the realization that you will form these centimeter to meter size solids that are able to drift in the disk, so they can be lost very rapidly onto the star, but they can also be accreted very rapidly by planets that are being formed. And then you have to include photoevaporation, ice lines, etc., etc. Fortunately, we now have observations thanks to exoplanets, and we can compare planet synthesis models of the like of Ida and Lane, Albert Mordassini, Benz, etc., to the observations. And this is one of these models attempting to reproduce the observed mass radius relation and being relatively good at doing so. Yeah. There's a big question also, which is how to enrich the giant planets' atmospheres. We've seen that all giant planets in our solar system are enriched, but it's not really clear right now how you deliver these heavy elements. Yeah. Of course, when during the core accretion phase, planetesimals reach the central core, and so you have a very efficient process in terms of accreting these planetesimals or pebbles. Then the envelope forms, and the planetesimals cannot reach the core intact, but they'll still be deposited quite deeper down into the envelope, because this is a very tenuous envelope. And then when you actually capture most of the envelope, the hydrogen and helium, what happens is that the accretion efficiency drops. And this is something we showed with Brett Glanman. So in order to explain this enriched envelope, what I proposed was that core erosion, so mixing heavy elements that are deeper down all the way into the envelope, would be an efficient way of doing so. And then at present, you'd end up with enriched atmosphere. There's another way, which is to, as you form these giant planets, you accrete efficiently planetesimals at the same time as the gas, but it's a bit hard to do, and to be able to make an envelope with a gradient of planetesimals that has the right properties, but we'll come back to that. It's very much an open question. So there's a lot of work to be done in this direction. Okay, so now let's talk about mission Juno, switch gears a little bit. So Juno was the first mission really to be focused on Jupiter itself rather than its moons. After Galileo, in 1995, the Galileo mission sent probe into Jupiter's atmosphere, aiming for the detection of water into the planet. But unfortunately, it didn't go deep enough, although it went much deeper than expected. And maybe we'll come back to that. And so it didn't find the bulk abundance of water in the planet. And water was really the essential molecule that Galileo was aiming for. So in the late 90s and early 2000, we came up with the idea that we had to go back to Jupiter and to look specifically at the planet. So Scott Bolton, PI of the proposal, it was initially a proposal named Jazzy. There was another mission called Inside Jupiter, another one called JPO. Everything was united into what became Juno and was accepted by NASA in 2004, 2005, was launched in 2011 to Jupiter and was inserted into Jupiter's orbit in 2016. So the idea there is to get very, very close to the planet. We're only 4,000 kilometers above the cloud tops. So that allows us to have a very high sensitivity to the gravitational perturbations of the planet, to its magnetic field, and also it allows us to probe the deep atmosphere, being inside the Io synchrotron belt that allows us to see deep in the planet, something we wouldn't be able to see from the ground. So the Juno is around Jupiter since 2016, and the orbits are 53 days long, and you see it's a very elliptical orbit. Recently, we're very happy because it's been extended to 2025, and the idea is that Juno will be able, as its orbit precesses, to probe the north hemisphere of Jupiter, and in particular its pole, where we have very nice vortexes. We'll see that later, and to study them is really, really important to understand the dynamics of this very complex atmosphere. So the spacecraft carries a bunch of instruments. So the Gravity Science Package, which is basically the radio link to Earth, a magnetometer, a microwave instrument that's able to probe the deep atmosphere, a visible camera, an infrared camera, and then various other instruments to measure the high energy particles and characterize the magnetosphere of the planet. So it's a big spacecraft. You can see that it's 18 meters in diameter. It's with its solar panels because it's solar powered, no radioisotopes. So it's quite an engineering feat. And everything has been working really smoothly since the launch. So the goal here is to see how we study the interiors of giant planets all the way to the atmosphere. So let's have a look at what we have in hand. So the idea with our theoretical models, of course, is that we'll simplify everything. We'll assume that giant planets are a big gray balls. We have, of course, their mass, their radius, their luminosity. We have an atmospheric temperature pressure profile. We have some ideas of atmospheric compositions. So we have boundary conditions. And importantly, we have rotation rate and a gravity field measurement. So that's the key parameters, key variables we have. Then we're using the same equations as for the stellar structure. So basically the hydrostatic equilibrium, the thermodynamic equation that is just a definition of this nabla T, but depending on the transport mechanisms, whether you're convective or radiative, this equation will be written slightly differently. And so that allows you to calculate temperature. Then you have mass continuity here, and then you have energy continuity here. So the luminosity added is equal to the production of energy in each layer and to the entropy loss in each layer. Okay, so in giant planets, of course, this production of energy is not due to thermonuclear reactions. You can include a little bit of radioactivity in the core, but generally that part is really negligible. So it's really that term, the entropy term, that's dominant. So that's another way of writing them as a function of mass instead of radius, but really those are the same equations. Okay, so when we have this set of equations, we have an equation of state that gives us density as a function of pressure, temperature, composition, and entropy also same as function of same parameters. We have almost everything. We need boundary conditions. So at the center, the boundary condition is obvious. But at the outside, we have a pressure that is a function of the gravity of the object and the luminosity to be transported, and the temperature, which is also a function of these parameters. So you can, for example, use an Eddington approximation that's used very much in the, or was used very much for stars in the past. Now we're using, of course, much more complex relations, but basically it tells you that there's a point in the atmosphere where the physical temperature is equal to the effective temperature. So the effective temperature is defined from the luminosity you have to transport. So it's a measure of the flux transported. And this point where this temperature, physical temperature, is equal to effective temperature is at a pressure which is equal to 2/3 of the gravity divided by the mean opacity. So gravity is in centimeter per second square, and opacity here will be in centimeter square per gram. So you can see that if you have a high gravity, so a planet that is very dense, then this pressure of the photosphere is higher. And conversely, if you have a high opacity, you have clouds, for example, or particles, then this pressure of the photosphere is lower, so at higher altitudes. Then. Okay, so generally we don't use this approximation. We're using an atmospheric model that links effective temperature to physical temperature at a certain pressure. Here, 1 bar is a very convenient pressure level to use. Of course, it depends on gravity also. So those are relations for Jupiter, Saturn, and the brown dwarf from the 90s. There's now better relations, but it's to give you an example. Okay, so how do we construct interior models? We use, of course, a phase diagram of hydrogen. Those are adiabats, or pressure temperature profiles rather than alibats actually, for the giant planets in our solar system here, and for this brown dwarf, Gliese 229b, for massive, I mean, exoplanet brown dwarf here, Coro 15b, or for HD 209 48b, which is a hot Jupiter. So you can see we're spanning a range of temperature and pressures. What's important here is that we are in the molecular regime for hydrogen, where above the solid to liquid transition here, or fluid actually, because we're supercritical. And also we have at about a million bar this transition between molecular and metallic hydrogen, but 4 giant planets were safely above this critical point. Okay, there's been some controversies on the equations of state. They have been mostly resolved now. This is the experimentally determined molecular to metallic transition. It's a smooth one because this first order transition has moved in the year 2000. And so from being here, theoretically, to lower temperatures. So there's no first order transition between molecular and metallic hydrogen. It's a smooth transition. Okay. In terms of energy transport, we believe that giant planets in our solar system are mostly convective. There was the idea that they may have a deep radiative zone. This is work I did in the 90s. But the discovery of alkaline metals in brown dwarfs has shown that this additional opacity source should block this radiative window so that the interior, these envelopes, should be fully convective. Now, the last ingredient that we have, and it's an important one, is that giant planets are fast rotators because they contract. There's some initial angular momentum that is not negligible. And because of that, they are flattened. So the polar radius is smaller than the equatorial radius. And we can measure gravity potential that departs from sphericity, so this Gm over R relation. And these departures are measured in terms of these J2n, which are called the gravitational moments. And these functions, P2n of cos theta is the co-latitude here, those are Legendre polynomials. So these gravitational moments are very important constraints for the interior structure. And this is why you can show that in a rotating frame, the hydrostatic equilibrium can be written as a derivative of this gravity potential times, minus or plus the centrifugal acceleration here. You can write this potential in that way as a function of the internal density. And the key here is that you can show that this 1 over r minus r prime depends on Legendre polynomials, can be expanded that way with an infinite sum of r prime over r power n times Legendre polynomial, and depending on where you are, inside or outside a certain layer, you have these two relations. So you end up with a rather complicated set of differential equations, but you can show that your gravitational moments that you're measuring are a function of the interior density profile times these Legendre polynomials. Okay, so it's a way to relate a measurement to a model. And so build models that are progressively better at matching the observations and hopefully reality. So the way we're proceeding is that we solve these hydrostatic equations with rotation to fourth order in that expansion on Legendre polynomials. We're calculating gravitational potentials, gravitational moments, theoretically matching that to the measured ones, and then constraining parameters like the mass of the rock ice core, the composition of the metallic and molecular region. And so we go on like that with, of course, all the ingredients that we have and the constraints that we have. These gravity moments have contribution functions that peak more and more outside the planet as you increase the order. So that here, when you look at the full mass of the planet, all the layers, of course, will contribute to the mass, but the most important layers will be at the center of the planet for a fixed radius. Then, when you're measuring J2, you're sensitive to more outer regions, and then progressively so with J4, J6, J8, you're probing more and more external regions. So the way we would proceed when building these models is from outside in. We have here a molecular region inside in Jupiter that's helium poor, and this is because helium is forming droplets in the planet, and so it's sinking into the deeper interior. Then we have a helium-rich metallic region, and we have a core, and all these are contributing both to the mass and the gravitational moments. So that's the way giant planets models have been constructed, and we came up with these kinds of structures for Jupiter and Saturn, with a core, a metallic envelope, a molecular envelope, and in between a helium rain region. And for Uranus, Neptune, we have something relatively similar, but they have less mass, so there's no metallic part, and we switch directly from a molecular hydrogen to a core that's made of ionic ice, water, and compressed high temperature ices. Okay, so that's the principle of modeling the interiors of giant planets. Now let's look at Jupiter's interior structure based on the Juno measurements. So the key here was to determine the gravitational moments, and in particular J4 and J6. And this is where we were able to make very significant progresses. So you can see here, this purple arrow bar shows the Voyager constraints on the J4 and J6 in Jupiter. Of course, Voyager was in the equatorial plane of Jupiter quite far, and so the constraints were rather loose. There were new constraints thanks to New Horizon, in particular, and Cassini, Galileo a little bit, but there were not, I mean, there were two discrepant values, and so it was not very clear prior to Juno's launch what we should use. With the first orbit of Juno, we were able to determine this very nice red arrow bar here. And by the sixth orbit, we could have something that was 2 orders of magnitude better than the initial constraint. And it's this very tiny yellow point here. So that's the level of improvement that we were able to reach. It's really something fantastic. Um, I'm going to show you that because we have to account for differential rotation, we have to fit a slightly different value of J4 and J6, but with these error bars, it's almost invisible here. The interior models were all lying in this region here. You see this green box from Nadine Nettleman, or the models Bill Hubbard and Burkhard Militer did, or what we did with Shamila Miguel. They were all lying here. But Sun Wall, as part of his PhD, found a nice way to show that you could come up from these models by Hubbard and Militer to all the way here by mixing the core partially in the envelope. So this is what happens when you change a little bit the entropy constraints and things like that. And then when you dilute the core into the envelope, it allows you to find another class of solutions that's matching better the Juno constraints. So this is very dependent on the equation of state. We were getting solutions with the old Rostock equation of state that didn't necessarily need this dilute core, but those have entropies that are now believed not to match the lab experiments. And so it appears that these kind of solutions are better reproduce the constraints that we have. Something very robust that we were able to find is that there's more heavies in the metallic region, and that Jupiter's envelope is not homogeneous. So this is something that is a very robust and strong result from Juno to be able to determine that. And it has, as we will see, a lot of consequences. So there's been various work on these aspects, on modeling the interiors of giant planets. And but basically all need an envelope that's not homogeneous. Okay. And this is now in line with some formation models. And I'm sorry, I'm going to skip that. In Saturn, briefly, there's been some significant advances as well, and this is thanks to seismology that's been done through the determination of oscillations in the rings of Saturn. We know that Saturn has some stable zones where G modes can propagate and interact with the F modes. This is very important work by Jim Fuller. There's very nice work recently by Chris Mankiewicz and Jonathan Fortney to show how this impacts how we view the interior of Saturn, with probably a helium gradient and a helium shell on top of the core of Saturn, and maybe a dilute core as well in Saturn. So now let's move to Jupiter's, how these heavy elements were delivered. If we have a dilute core, it's not necessarily obvious how you do that. One way, and this was shown by Mikhail Lozovsky, and then with Alona Vazan's work, that for which I contributed a little bit. If you have an initial compositional gradient, then you will mix progressively the envelope. But if you start that at a low enough temperature, then you can retain this initial gradient of heavy elements and form this staircase structure. I'm going to show the movie again. So that's what's happening. So you're convective here, and you're forming these various convective layers that are sandwiched in between conductive layers here. And so within the case of this simulation that doesn't include double diffusion, this is what we're getting. So this is a way to explain the Juno observations and see also the work by Ravi Teled in particular on this kind of models. So basically, we'll end up with an inner core that's dense but very small, and then a dilute core in which the heavy elements content can change by a few to several tens of percent, and then an outer envelope that's mostly hydrogen and helium with noble gases and some heavy elements. But it's not necessarily easy, in fact, to get this composition gradient in the first place. So Shanfei Liu has come up with an interesting idea. It's a little bit the last resort when you can't do anything else. You rely on giant impacts. And he showed that if you have a Uranus mass planet around 10 Earth masses that impacts a young Jupiter, then and you have a head-on collision, then you can actually partially mix the core with the envelope, and then you have the gradient that you need to explain this dilute core and the Juno observations. So that would be able to explain both the dilute core and the enriched envelope, because you're mixing up these elements that are deeper into the interior. However, recent work by Simon Muller seems to show that the initial entropy is high when you're forming Jupiter. And so in that case, you tend to mix everything. You're very efficient at mixing if the initial entropy and temperature is very high. And so maybe we're back with a problem again. So this is still TBD. Now let's move to a slightly different subject, and it's Jupiter zonal flow. With the gravity field, we're able to put constraints on the rotation of the planet. And this has been something that's a long time mystery for more than 40 years. From this animation, this time-lapse movie that's been done with amateurs, you can see that Jupiter is not rotating at the same way. It's a fast rotating planet. It's rotating in 10 hours, but some regions are rotating slightly faster by 1 or 2% than the others. For example, the equator is rotating faster by 100 meters per second than the rest of the planet, and then its magnetic field rotation. Yeah. And so the big question was whether this was simply skin deep and you just have this weather layer that rotates in this particular fashion, or whether this was proceeding deeper. Theory tells us that because we have a small Rossby number, we should have rotation that's constant on cylinders on average, and maybe this should proceed very deep into the planet, so the whole planet would rotate on cylinders. Well, thanks to Juno's exquisite measurements, we've been able to put a constraint on that, to measure the depth of these flows, and this has been published in 3 papers in this same issue of Nature. And by the way, those are the magnificent polar vortices that were seen in the infrared by Juno for the first time. And this is something that remains a mystery. But the first point that I'm going to talk about here is that we've been able to see that Jupiter's gravity field is north-south asymmetric. So Bill Herbert had published in the 1990s this very important paper showing that if Jupiter rotates as a rigid body, or if this differential rotation is just skin deep, then you should expect a gradual decrease of the gravitational moments as a function of harmonic degree. But if you would have rotation on cylinders involving a sufficient amount of mass, then this would plateau and you'd end up with gravitational moments J10, J12, J14 being of the same order. We were not able to use this method because the formal uncertainty of Juno's measurements is too high, but we've been able to measure odd gravitational moments. So it means that we're able to see asymmetry between the north and the south in Jupiter's gravity field. Okay, and this is something that you can show as a map. When you filter out the first gravitational, even gravitational moments, you can see that here this band doesn't have this counterpart in the south. So we really have something that is asymmetric. So because Jupiter is a fluid planet, the only way really to explain that is to involve these zonal flows and invoke that they involve enough mass so that you have a gravitational signature that's large enough. And this is because Jupiter's zonal winds are also asymmetric. You have this jet, this north equatorial jet that is very prominent and that you find here somehow in the gravitational signature as well. Okay, so this was a sign really that the zonal flows of Jupiter were extending deep enough into the planet to involve sufficient mass. Then my colleague Yohai Caspi was able to analyze the odd harmonics thanks to a method that he really pioneered and that involves this thermal wind balance in which in a rotating system you show that gradients, horizontal gradients in the zonal flow, this U here, that's the gradient of U times the rotation vector, which is vertical on Z. So you have just a horizontal component here that matter, has to be balanced by a gradient, a vertical gradient in density. Okay, so if you change the zonal flow and somehow if you have a zonal flow that has to decrease somehow at depth because you have the magnetic field that will force everything into almost uniform rotation, then you must have a gradient here. So you must have perturbations to the density in the interior of the planet. And so by tying these two, you're able to constrain or to calculate perturbations on the gravitational moments that will depend on the depth of the penetration of these zonal flows, which is H here. Okay, so if you draw that, these Jn values change as a function of depth into the planet. So you, from a very small number in absolute value to much larger ones as you increase the depth of the flow. And interestingly, and this is a property of the Legendre polynomials themselves, they switch sign. And this is something very nice because we were able to show that the J3, J5, J7, J9 have the same order of magnitude as predicted and the same sign when h is of the order of 2,000 to 3,000 kilometers with this simple model in which you have a zonal flow that decay exponentially with depth. Okay, so this was a way to constrain the depth of the flows directly from the odd gravitational moments. We were able to do that also from the even harmonics, but this is a little bit more or less straightforward, or I mean, nothing is really straightforward there, but it involves both interior models and differential rotation, because there's this degeneracy between the unknown interior structure, the unknown composition of Jupiter, and the unknown differential rotation, which you don't have for odd gravitational moments, because we don't expect an asymmetry in the composition of Jupiter deep down, because it's a fluid planet. So we had to use a large variety of models, play with all the different parameters of the models, and to look at all the constraints on J2, J4, J4, J6, J8, J6, J8, J8, J10. Those are the possibilities with differential rotation, with different depth of differential rotation, and those are the models. Okay, all the models that we constructed, you can see that in J2, J4, we can have anything, but then in J4, J6, we have a correlation between those moments, and that enables us to constrain the depth of differential rotation. You can see that we're going in and are compatible with the blue squares, but not with the red ones. So it means that differential rotation has to be has to extend to less than 4,000 kilometers. And we're offset also here, so it means that there is some differential rotation. So you calculate the maximum likelihood with all these models, and you end up with highest likelihood with a depth of the wind that's around 3,000 kilometers. So it's a nice agreement with what we found for the odd gravitational moments. And interestingly, this is a zone in which the electrical conductivity of hydrogen is increasing a lot. You see the scale here, it's orders of magnitude. And here we have the conductivity of salt water in the ocean. And this is where it had been shown that ohmic dissipation would become too important if we had too much differential rotation, and so it would create more energy than Jupiter's luminosity. So that's a limit. I mean, we can discuss on whether this is a strict limit or not. There's recent work by Wisht et al. In particular that's very interesting on that. But in any case, at some point around these levels, remember the electrical conductivity is increasing by orders of magnitude. We have to decrease the differential flow and to be close to uniform rotation. And indeed, this is what we're finding. So the picture that we have now, thanks to Juno, is an outer layer that's molecular and that's differentially rotating. Then 3,000 kilometers below that, you have something that's conductive enough to be mostly in uniform rotation. And then you have metallic hydrogen, where really the magnetic field is created deeper down. And we've been able to apply that to Saturn and to explain the Cassini measurements as well. In Saturn, which is a less dense planet, the zonal flows go deeper to about 9,000 kilometers rather than 3,000 in Jupiter. Okay, so there's ongoing work on that. It's not the end of the story. In particular, there's no theory at the moment that predicts exactly where the magnetic field should damp differential rotation enough. It seems it's not powerful enough to do that at this depth. So we're still investigating the issue, but qualitatively, I think it's a great leap in our understanding of differential rotation in giant planets in general. Okay, and then the last result from Juno I want to talk to you about, which is very significant, is about Jupiter's inhomogeneous deep atmosphere. And this is something that we found with Juno's microwave radiometer. This is a picture showing both Jupiter, this small tiny layer which is expanded on the right here, which shows a map of ammonia abundance. Blue is very low abundance, red is high abundance. And so you see that we have variations as a function of altitude, but also as a function of latitude, with the equator showing this kind of plume of very high ammonia abundance and the higher latitudes not showing this. This was very surprising. It had been seen from the ground thanks to the VLA, but at much lower depth. And with Juno, we've been able to extend that to great depth. And it's a great surprise that it's ongoing to tens of bars, 200 kilometers, maybe deeper, we don't know. And this is something that's very robust. We're seeing that at every perijove, again, NH3 abundance, latitude, and this is internal pressure. So you're deep here at the bottom of these diagrams. You're seeing the same feature on, and with a depletion in the North Equatorial Belt that's very significant and proceeding very deep. So we struggled to come up with an explanation for that. And this is what I think is a key ingredient. And this is a phase diagram from water and ammonia showing the partial pressures of the two. When you combine them, you can form solid phases in gray. So you have, for example, solid H2O that we know and love. Here in this diagram, you have in vertical lines, or almost vertical, the temperatures. So you can see that we have here a liquid phase, and we're freezing water. So that's good when we have very low ammonia abundance. But when we have a high ammonia abundance, things begin to change, and they change at low temperatures. So ammonia is a very powerful antifreeze, so you can have liquid ammonia water down to -100 Celsius. That's what's shown here in this diagram. And by the way, this comes from Lewis, 1969, and Waddell, Chilling, and Lewis, 1973. Uh, so in all this region, you can form liquid ammonia water. And with the Juno ammonia measurements of the ammonia abundance, we have a constraint on where we are in this diagram. So the high value of the ammonia abundance is here. The low value is seen by Juno, the average value after you've condensed, after you vaporize the ammonia is that one. So you can see that we're passing through this very interesting region where we can form a liquid H2O and H3. Okay, so in a storm, for an ice crystal that goes up in Jupiter, a water ice crystal, you can reach this region at high altitude and the ice crystal will melt and will become what we call a mush ball. So a sort of water ammonia hailstone that's able to grow, we believe, to 10 centimeter size, and to go very fast deeper into the planet. And so that's a new mechanism to transport ammonia and water into the deep atmosphere of the planet. So in this region, we're forming these liquid mush balls. And now I'm just going to show you an artist's conception of this mechanism based on the Juno observations. So we're going into one of these storms. You're seeing these little ice crystals, and then this mush ball forms thanks to the absorption of ammonia vapor. We have lightning. We've observed shallow lightning at temperatures of less than minus 66 Celsius. So we know that there must be liquid present. So these mush balls must be forming. And this is how they go down very rapidly, and then they evaporate. And when they evaporate, you're still left with something which is cold and dense and can sink further down thanks to downdrafts. So you can really transport ammonia and water efficiently deep down into Jupiter's deep atmosphere. So this is a mechanism that I proposed in these two papers last year, and we have a paper led by Heidi Becker showing that it explains also the presence of shallow lightning detected by Juno. Interestingly, we're able to reproduce the NH3 map as a function of latitude and pressure if we change the frequency of water storms in Jupiter. So that's the black line here as a function of latitude. And so we have to invoke the fact, for some reason that we don't explain, that there's very little storms near the equator and much more frequent storms elsewhere. And interestingly, it matches the amount of flashes per second that are measured by Juno MWR as a function of latitude. You see very few flashes at the equator or none at all, and more lightning in this region, especially where there's a lot of ammonia depletion, where ammonia is transported very deep down in the planet. So it has consequences not only for ammonia, but also for water, because water is, of course, part of this mechanism. So we are predicting that water should be transported downwards to great depth. We can't predict the abundance because this depends on the efficiency of this mechanism and it's not known. But it really relates to the Galileo probe measurements. I was telling you earlier that the Galileo probe measured a very low abundance of water in this region, and this is exactly where we're finding that water should have low abundance everywhere, not only in this particular spot called the hotspot where the Galileo probe fell, but in all these regions in these latitudes. So it has consequences for giant planets in general, because in planets with hydrogen atmospheres, condensates are always heavier, okay? And when concentration mechanisms exist, uh, these condensates can sink and will sink, okay? So vertical composition gradients may be formed, and this will lead to regions that are stable on average. So it changes the picture, really. For very high abundances of condensates, we have another phenomenon. It may be occurring in Saturn, and certainly it's occurring with methane in Uranus, Neptune. Moist convection is locally inhibited. This is something I had shown in the 90s, and that's been revised by Jeremy Lecomte and Jim Princeton in particular. So it means that the resulting temperature composition profiles are unknown. And then there's the big question: how deep do those condensates sink to? And this is unknown. This is really unknown, even with Juno measurements, because we don't have enough information coming from the deep reaches of Jupiter. But a mission to Uranus and Neptune would be able to tell that, certainly for the methane cloud, because it's occurring much higher up, and so we will be able to characterize it much more precisely than we can do that for the water clouds in Jupiter and Saturn. And this is a small experiment that you can do in your kitchen with water and milk, and you can see that with just a drop of milk, although equilibrium chemistry would predict that milk and water are very happy together and can mix, you'll see that you form a plume, and that this plume sinks because milk is heavier than water, and you're creating a gradient that can last for a very long time. And I believe this is something that's very akin to what's occurring in Jupiter and Saturn. We have signs that this is the case in Saturn as well. And maybe Lee Fletcher's lecture will deal partly with that as well. So of course, there are consequences for exoplanets. We have a more complex planetary evolution. We have to account for core mixing. So part of the internal heat will be used to mix the core upward. So this will lead to a relative increase of the gravitational potential energy. We have deep compositional gradients that can lead to a possible suppression of heat transport and a late release of internal energy. We modify the atmospheric properties because of that. So how do we link atmospheric abundances and deep ones? How does it affect the cooling of the atmospheres? This is a sketch showing the standard adiabatic evolution models. You have a core that's thought of being relatively inert, okay? And then as a function of time, you will have entropy and temperature that go down, and you follow an adiabat because you're fully convected. That's really the standard picture. And you're controlled by the atmosphere here. But now we have these two effects. We have core erosion that leads to a decrease of the available potential energy. So it means that you're taking this potential energy to mix the heavy elements, the core or anything. And so the end result is that you have less luminosity and so a lower temperature for a given time. So generally, you will have a faster evolution with that. And then you can have, because of this composition gradient, a non-homogeneous evolution. So if you, in that case, you have various phenomena that can occur. So initially, you will have a faster cooling of the outer layers. And this is because the inner layers are not contributing very much to the luminosity. So you're cooling the outside more rapidly. But then once you've cooled the outside sufficiently, then there's a lot of heat that has been stored inside. And so the sense of the mechanism inverses, and so you're slowing now the evolution because the inner layers are contributing. So this gives rise to important changes in how we view the evolution, and of course the changes in atmospheric boundary conditions because of the different or evolving composition will also affect the evolution. Okay, so in order to solve that for exoplanets, of course, measuring accurate ages is key, and this is something that Plato in particular will do. We need to understand planetary cooling. We need to realize that temperate giant planets in particular should have complex atmospheres, especially when water is condensing. It's very powerful in creating storms and in transporting major species downward, so to create compositional gradients. So this is something which we should be able to test, and which will be important for the analysis of data. It's true for giant planets, for gas giants, but also, of course, for ice giants, and of course, for super Earths with hydrogen atmospheres. Okay, so there's questions and opportunities. Do giant planets have cores? We can address that question by measuring K2 in some very specific exoplanetary systems. So this is the second love number. Are they enriched in heavies? Again, we will use a bunch of measurements. Again, we will continue working on Juno, even Cassini data. And of course, we're expecting a lot from JWST, Plato, and Ariel to characterize the atmospheres and link to the deep interior of these planets. And then the same kind of questions, how are those distributed in the interiors? There's various ways of addressing that. And then what is controlling the atmospheric circulation in gas giants? Again, we have a chance that with these giant planets, these hot Jupiters in particular, we have the ability to constrain the dynamics, the winds in these planets. Even for planets that are further out, we had a determination of the rotation rate of beta peak B, which is really quite a feat, quite amazing to see that that was possible. So we do have constraints there. And then to understand how planets form, we need a combination of everything. So strategy is really to go for more statistics, and to discover key targets in terms of the exoplanet population. But we need also to combine that to theories of the evolution of our planet. Sorry, Nelson, I'm a little bit late.
Bonjour.
Sorry for that. So the last thing is really that we need a mission to Uranus and Neptune. And this is because these two planets are really the missing link to understand Jupiter and Saturn and exoplanets. With a mission dedicated to Uranus or Neptune, we can characterize their methane clouds, understand the behavior of these condensates in a layer that we can probe very easily, because methane is condensing at around a bar. It's very abundant, and we can do lots of things. We can measure gravity field, magnetic field, maybe even do seismology. So to understand the dynamics of hydrogen atmospheres, learn how planetary interiors constrain the origin of the solar system, and really understand how giant planets form. And this can be applied then to exoplanets. Of course, there's a lot of cross-feed between the fields, but in particular, we will be able to refine our evolution of the models of the ice giants, in particular the atmospheric models, and this is very important to interpret the spectra that we're getting, and then really understand as a whole these new worlds that we're discovering. So a lot of things to do, and thanks for um, having listened to this presentation, and take care. Goodbye.